Pierce and Peterson, both from RDG Planning Design out of the Point office. They're going to be, the presentation is titled Over Land, Water, Air, and Cyberspace Using New Resources in Watershed Planning. So we're going to hear about some new technologies that they've been using in the Walnut Creek Watershed Plan down in Walnut. Greg joined RDG in 2014 as a water resource engineer, and he's focusing on integrating effective stormwater management projects from site level to watersheds. Ryan Peterson is a landscape architect with RDG, and he focuses on connecting people to place through the integration of natural systems within the built environment.
Good morning. Wow, I was going to ask, can everybody hear me? But I guess I've got their answer right. Okay. That's a little bit better. Okay. As was mentioned, I'm Ray Pierce with RDG Planning Design. Ryan Peterson is also going to be part of our discussion. I'm a water resource engineer. I'm licensed in 6 states here through the Midwest. And stormwater has been my passion for the last several years, managing stormwater more effectively, trying to rebuild some of our arterial stream corridors and deal with water quality issues. Today, we're going to talk real briefly about some of the newer technologies. Some of these aren't all that new, and some of them are. Methods that if we were doing watershed planning, a decade ago, 15 years ago, 20 years ago, we just wouldn't be able to do these things. These things we'd have to make a lot of assumptions and a lot of guesses of what's really going on out there. But now we have the tools to do planning a lot more effectively and a lot greater detail. So some of the things we're going to be talking about today are, things like using quadcopter technology, using GIS tools, water quality modeling, and then how do we prioritize using these resources. So one of the first things I'm going to show you, if it'll let me. Yeah, set up the show here. All right. So this is video that we took in December of 2014 from a quadcopter. This is Walnut Creek in the city of Urbandale running through one of their parks. And we actually had a pretty interesting reaction from some of the people at Urbandale to this video. They're like, oh, that's our park? And they saw some of the conditions that they didn't even really realize were there, so it was the city officials. But you'll see this bird's eye view really gives you a lot of a different perspective that we don't usually see if we're doing assessments on the ground. Through the vegetation patterns and the sediment deposition patterns, you can see really where the stream is flowing, where it's gouging out. These are things that we can see to a certain degree if we're doing an infield assessment, but maybe really difficult to pick up on some of these patterns of flow. Here you see a video we took. There's the actual quadcopter itself hovering over the stream. You can see that kicks out quite a bit of force. You can see the water getting stirred up below it there. So if I was standing on this bank, I really don't know in detail the conditions of the bank below me. I know it's high, but I really can't see the conditions. So if I was going to do this assessment in the field, I would probably have somebody working the opposite bank too to photograph this really well. But you can see here, this is the perspective we're getting from that camera and what's really going on our feet. We learned later we probably shouldn't have been standing so close to the bank that day. But you can see the rapid down cutting. A lot of this is live grass that had fallen off that previous year. So it's, there's active erosion in this area. You can see quite a bit of scour along here. You can get an idea of the depth of the flow. This is frankly a perspective unless we're actually wading in the stream that we would just have. So now we have the bird's eye view. We're actually getting way down, literally floating above the water and able to assess the stream in this manner. One of the benefits of this technology too is that we can actually program a flight path that it can repeat over time. So if we wanted to fly this path and then come back in 3 years, 5 years, and do the exact same flight path again, we can see the changes in condition over time. That's one thing that's very deceptive in a lot of our urban streams is people don't realize how fast they're changing. I mean, you're there 1 year and then you don't look at it. Maybe you come back later and you don't realize, oh, this has changed a lot in 4 or 5 years. Well, now we can actually have video evidence of, okay, this is what's going on, and we can come back later. As an assessor myself, I can go back to the office if I'm doing assessments. I don't try to remember what I saw that day and try to piece it together from photographs or field notes, I can just watch the video again. Be like, oh yes, this is how it was that day. These are the conditions I saw. This is really where it was. So that's very, very valuable to me as an assessor. Some things that are coming down the line too, you can actually use the photographs that the quadcopter takes and actually build surfaces from them. So it takes a series of... I'm going to turn that off. How's that? That's fine. I will try to project. You can actually take photographs and build a surface from those, from a series of photographs and render basically a 3D surface. We've also seen other people that are using it to scan like pebble sizes in the stream to get the distribution and the idea of what the bed material of the stream are. So there's a lot of potential applications for quadcopter technology. I'm going to turn it over to Ryan to talk about some ways we've been using GIS on a variety of projects.
Thanks, Greg. GIS is another tool that we've been using for the past probably 10 or 15 years or so to really help us do a desktop assessment before getting out in the field. And I'm sure many of you are aware of the technology, but really we're trying to use a systems approach that informs our field exercises. And so we're not just shotgun blasting and going out there and saying, you know, we're going to walk this corridor. We recognize resources are limited, and so we want to be as informed as possible. So the example on the screen here is from Walnut Creek Watershed down in Kansas, and you have 3 different layers, and essentially what we're doing is we are assigning a prioritization scale to the wetlands, lakes, and streams on the left-hand side, looking at the slopes in the center, and then also how the existing vegetation, how all of those things, if you roll them up and assign a certain prioritization to each of those characteristics within the watershed, will inform the decision making here. In this particular case, we're looking at where are the best areas to develop or where are the best areas to avoid. You can take that actually down to the site level. As many of you know, the soil surveys that were done or are continued to be done and updated provide a good baseline for making planning decisions. And so we're trying to stay at that 40-acre scale or maybe down to the 20-acre scale within this. But in this particular case, there was concern over a lake that had been polluted before, and a 15-acre development of an intermodal facility was going to go in. So they were wondering, how can we plan this out in the future without further degrading that lake? And so, as you can see here, essentially those natural systems that are at site directly inform the layout, if you will, of the master plan, identifying areas to avoid, areas where we can potentially mitigate, and then those opportunities to fold in green infrastructure to manage the stormwater on site. Really, another approach that we've used has been more on the natural resources side. And so what we're trying to do here is identify a very clear objective up front. We're trying to solve a very specific problem. So in the case that I'm going to show you here in a minute, I'm trying to identify where the tall grass fenn ecosystem may be found so that you could potentially preserve those areas. And so what we do is number one, we identify our objective that we want to achieve. And as I just said, we're trying to find the tall grass fenn. Secondly, we're looking at the research that has been done, not necessarily research that we're doing in-house, but there has been a lot of amazing research done by our institutions and also some of the non-governmental organizations. And so using that to inform our decision-making before we go out in the field. We then develop suitability modeling or weighting, what each of those factors, how they input into the model and which are worth more than others. And then develop the model within GIS, and then obviously go out in the field and verify that what we think is happening in this area that we think it should be is actually happening. So there is a bit of ground truth. So in this particular case, it's probably a bit difficult to read back there, but essentially we had 4 different criteria. So we're looking at trying to identify in the landscape where a tall grass fenn is located. So number 1, typically they do the research that's been done on soils that have similar characteristics of muck. So that's a key thing. Secondly, areas where ephemeral wetlands have been found based on the National Wetlands Inventory. So we can use that information. The third thing would be typically a tall grass fenn is located at the toe of a bluff. And so all of the research that's been done tells us that based on these characteristics, there's a high probability. And so then assigning a weighting, and then on the right-hand side of the screen, when you roll that up and give it the numerical scale, it very clearly articulates that here is an area in red that there's a high likelihood that this is a tall grass bed. And so on a large scale, on the 40,000 acre or 50,000 acre scale, you can very quickly start to identify where those sensitive habitats are, and in this case, where you might be looking to preserve them. Greg, do you want to talk a little bit about how we're using the LiDAR to inform the watershed planning?
Sure. We've been using a lot of these tools on the Walnut Creek Watershed Plan. It's a 53,000 acre watershed in Fulton, Dallas counties in central Iowa. And we're using a lot of these tools in our planning effort to develop a consistent plan. You can see here, one of the first things is taking LiDAR data that's available out there and looking at it and using it to find where are our streams, what are the streams that have already been mapped, where are areas that haven't been mapped before, and what are the watersheds, what are the actual areas of land that drain to these streams, how big is each little watershed area of each of these streams. So taking that down and not only mapping out those first and second, third order streams that we've already known about, but all these little lines in purple are little streams out there that are running through farm fields, that are running through areas. I mean, some of them aren't really even streams at all. They're just patterns of concentrated flow that flow through different farm fields or grass swales or things like that. So from each of these, we can gather information and use it to affect all our modeling and analysis. And we can take that down into a smaller sub-watershed or even micro-watershed scale. Here we're looking at a case study area in a rural area northwest of the Des Moines metro. So you can see this about 6 square mile area that we're looking at in a lot more detail. And we can use high resolution photos to map out not only where these streams are, but what are the conditions along these streams? What kind of buffers do we have? What kind of land uses? You can see down here, we've got pasture lands. Up in these areas, we've got row crops. We're nearing the edge of the community Dallas Center. What are all the land uses of the watershed? What are we seeing? Where are our buffers? Where do we need to make improvements? Where do we have filter strips? All these things then we can use to inform our stormwater modeling and do modeling in much greater detail than we've been able to do before. So all those cases, looking at the stream bank stability, we actually had both County Soil and Water Conservation that did field assessments in the stream. So we're able to map those conditions into this watershed and note which of these smaller micro sheds each of those cases were. So we could actually figure out how much stream bank erosion are we expecting in this little sub-watershed area. How much gully erosion are we expecting in these areas? So we can put all those parameters into our water quality models. And things like slopes and soils are also very important. So again, you can see this is derived from the LiDAR mapping. The areas in green are very, very flat. And we start to get to the areas in red, that's where our steeper slopes are. All those impact the amount of rates of runoff and the potential for erosion and the potential for pollution leaving our sites. All this information then we can quite effectively export into Excel files and export it directly into water quality modeling software. This is a program that's called Stepple. It's a spreadsheet-based program, but there's a variety of other water quality modeling programs that are out there as well. But we can take that, instead of having to hand enter all this data in a very time-consuming fashion, we can export these things, rearrange the columns, and have it just draw this information right into the modeling software. So we can take this information and actually learn, well, what is going on? What are the sources of pollution? So you can see in this case, for the overall Walnut Creek watershed, we can see that our nutrient loadings are expected to be highest from our cropland areas. From our cropland areas. So up in here, 80% of our nitrogen pollution in the watershed is expected to come from cropland. We're seeing a much different result on sediment. We're expecting that our highest loads are from gully and stream bank erosion. When the streams actually move and erode, it kicks a lot of the sediment. That's a source of a lot of the sediment we're seeing. So the changes of hydrology in the watershed that are causing our streams to destabilize are one big source of sediment erosion. So if we can address that, we can reduce the sediment input into the stream quite a bit. We were also able to evaluate through looking at land use maps and comparing conditions from 10 years ago to today, how fast the watershed is developing. We were able to determine about 6 square miles of land in this watershed developed over that 10-year period. So about 8% of the watershed. This is a very fast developing watershed, probably the most rapidly developing watershed in the state. So it went from about 35% urban to about 43% urban in only a 10-year period. So big changes. So we can figure out, well, on an annual basis, then how much construction site exposure do we have? And what would we expect the construction loading, site loading from those areas are, especially when we go out and look at some of these sites and see that in some cases they aren't doing a very good job of managing, keeping that construction sediment on site. We're able to figure out as much as a quarter of the total sediment load, and we're thinking the total load is about 30,000 tons a year. A quarter of that could be coming from these construction sites that only make up 1/10 of 1% of the watershed in a year. So that is a quick hit that we can do if we just better manage our construction sites, that we can do things there. So again, from GIS analysis, that's the information that was quickly able to run a model like that. And then we're able to then take that modeling information and export it right back into the GIS. We can figure out and show people where do we expect that our nitrogen loading is coming from. And the areas in green are our lowest loadings, and the areas in red are the highest. So again, our earlier modeling said, well, we expect the row crop to be the higher contributor to the nitrogen loading, so this map kind of confirms that. You can see that those sub-watershed areas show the highest loadings. Our sediment loading, again, we said gully and stream bank erosion are one of the two largest contributors. So where we saw areas with more gully and stream bank erosion, that's where the mapping is showing that the highest loading rates are from. And I should mention on this map, we specifically did not include construction site loading in this map. And the reason for that is that's a load that moves over time. We would be looking at where the construction site loading was over the past 10 years rather than where it would be moving forward. So we just screened it out and looked at just the gully and stream bank erosion and the other sources like cropland, some of the other sediment sources with that mapping. We're also able to take that information then and look at in detail, get a table and say, well, within each of these little sub areas, here's what we expect those loading rates are. And the importance of that is we're able to then say, well, where should our practices go? Where should we prioritize our funds? Where should we spend our money to get the best bang for our buck? We can actually go in and say, okay, well, our sediment loading, a lot of it's from stream bank erosion in this sub-watershed. We should make that part of our plan. And some of our higher loadings for nitrogen are in these sub-watersheds. We should try to distribute more of our best management practices there. So we have a better performance. We get the best bang. We get the best results for the smallest amount of investment. I'm going to turn this back over to Mike.
One of the key things is obviously Greg has outlined that within Walnut Creek there are a number of items that are going to require much attention. We can't just go in the next day and fix it. This is, it's taken us 150, 200 years to get where we're at. It'll probably take, hopefully we'll be able to turn the favor quicker, but the reality is that resources are slim to none right now in this area. And so one of the things we want to do is, for those areas where we know we can go in and address some of the issues, and the case we'll show here is related to stream stabilizations, how do we balance and select those areas using objective focused results. So we're trying to balance our criteria to get a very specific area that needs to be addressed to get the biggest return. This is based on the field information. Greg mentioned that the district, Public Soil and Water Conservation District, did do a RASCL assessment for a significant, almost 40 miles of the Walnut Creek itself. Greg himself has actually walked probably 15 miles of a segment that runs through Clive. And so we have some good data that tells us how high the banks are, how quickly they are eroding, things that can really inform us in making decisions. We're really looking to try to find the key areas of concern. Again, I mentioned that to get the biggest return. And then we're also using this as an opportunity to look for conflicts. In the case of the Clive Greenbelt, the project that is within the Walnut Creek Watershed, we're trying to target, where are those areas where Walnut Creek might be quickly encroaching upon the trail, or where is there a sanitary sewer crossing, or where is there a water main that might be in jeopardy, or where might there be places where public property, or actually private property, the citizens' property, might be in jeopardy from eroding away. There are a number of complaints, there are a number of things that go into doing that will help you inform why you choose to do stream stabilization, but we wanted to try to find a way that was objective and at a larger scale so that you can make an informed decision to get down into the site. And so what we did is we actually developed a model, and using the watershed data, we looked at key areas such as, I mentioned a few of them, we're looking to try to find out within the Clive Greenbelt where Walnut Creek and its relationship to utilities, where the creek is actively encroaching on on these utilities. And so we were able to develop a numeric scale that says, you know, if you have a 8-inch diameter water main or a 24-inch diameter water main, obviously there's a cost that goes with those. Also, that elevates the priority that you might need to address that specific pipe or that specific utility. We also looked at where is the trail being encroached upon by Walnut Creek, or where is the trail, is it too close? Looking at areas where the bank height is, whether it's 0 to 5, 5 to 10, or 10 to 20, where is that bank incision, or where is the stream incised? How does that inform where you go out and do stream stabilization, or where you restore the greenbelt? Looking at how the stability that has been noted through the RASCL assessment. So combining bank height with bank stability, it tells us where that almost 40% sediment load is coming from within the modeling that Greg talked about earlier. And then we're also looking at, again, the proximity to private property, the land cover, and then last but not least, the stream movement. We're actually able to digitize Walnut Creek, as Greg mentioned, through the quadcopter portion moves. And we all know that streams move, but sometimes you don't realize that the stream is actually 200 foot away from where it was 50 years ago. And so through the course of our desktop assessment, we're able to map the flow paths and get a good sense of where it's moving in greater extents than others. And so that will also help inform the decision. It's kind of like your investment. Past performance doesn't indicate future results, but we feel informed at least about making that decision. And so there's no guarantees, but when you look at the trends long term, you can see that the stream is moving in areas more so than others.
And one way we do that is by looking at historical photos. So looking back at photos from the 1930s and 50s and 60s and actually mapping out where that stream's been. And there's some areas where it has moved a lot, even some areas where it's moved a lot in the last 5 to 10 years.
So effectively, again, using weighted criteria, what you can do is you can quickly apply a numerical scale. So just for the purpose of conversation, about 18% of this suitability model or this prioritization model was given towards utilities. They're obviously a big concern. 18% of the overall model was applied towards stream bank height. 18% ended up being applied towards stream stability. 18% towards how much it moves on an annual basis. And then the remainder was made up of the trail proximity and then also the vegetation. And the weighting on that had to do with the cost to go in and do stream stabilization or the potential cost that might arise. And so the results are, and this is a work in progress, it's not perfect, we're in the beta version of it, but we've developed this model that effectively we can use as we're doing the Greenbelt Master Plan to project out where those greatest areas of concern are. So if we know we're going to do trail resurfacing in the area from Interstate 35, this happens to be Hickman Road for those of you who know this area, and then 128th Street. We know that within this zone there are a number of areas where the trail is in conflict or the stream is in conflict with that trail. Well, let's not just go back and pave that same exact trail in the same exact location. Let's make provisions to adjust the alignment. Or if we're going to go and do a sanitary sewer upgrade, and we need to think about where are those sewers in most jeopardy, we can use this to help inform that decision-making process. It's interesting to note on here, though, you can start to see the dots here effectively, wherever the dot, just due to the limitations of our GIS software, we were not able to necessarily, have a line down the center of the stream that tells you exactly where the exact distance of movement is, but the dot shown within there will do that for us. So effectively, we have where it shows these red dots. We have the stream in this location has moved over the last 150 years up more than 200 feet. So it's actively moving, and you can see here we also have this dark orange is showing that this is a significant area that we need to address, and it's primarily driven to how much the stream has moved, how high the bank is, how stable the bank is, and it starts to tell us that picture of, okay, well, this is an area we need to address. But then further on down, you can start to say, okay, there's an opportunity where the stream and the trail are in conflict. And then you start to look at where are there utility crossings, and so all of those different areas, when you fold them up, and I'm not going to get into the details of how GIS works, but essentially it's on a pixel by pixel basis. So the value or the sum of those pixels within and along the stream corridor, the greater the value, the higher the problem, or the greater there's a problem. What am I trying to say? The more likely it is that there is a problem, those are the areas you need to address first. And so all the way from using that watershed data at the very beginning that Greg was talking about, and then rolling it up with very specific data to help start to help municipalities or communities start to really plan out where they can invest their dollars so that they are making informed decisions. And so we think that based on all of these tools, moving forward, this will only get better and better and better, and we're quickly advancing some of the technology related to using that pictometry, if you will, to look at that stream corridor itself that you could capture from the quadcopter footage. So with that, I think we have 4 minutes where we can take some questions and maybe revisit some things. So, yes?
Where do those points along that stream come from? Is that manual data collection, or is that overlaying of layers?
It is a little bit of both. So we have the collection from when Ray did the Rascal assessment, so we were able to map out the exact flow path in 2009 and then in 2014. But to get the historic data, we digitized the flow path from the General Land Office survey, the 1930, the 1950, 1970. So we had to go through and manually enter all that data to tell us, what's happening. So it was a combination of when we did the Rascal assessment and then also the desktop.
I'm going through and doing that right now for the city of Marion, looking through just the DNR historical plans, and just trying to figure out where Indian Creek was and where it is now, doing exactly what you're doing right there. So,
yeah, it's very powerful and valuable if you're looking to make decisions down the road. So,
I got a major sanitary sewer trunk line that is going up the Indian Creek watershed all the way up to this brand new huge ballpark development. So as those pipes get planned, and it's going to be several years away, but as we start to dig around Indian Creek, I want to put some of these oxbows back as they fill that back in.
I saw spatial analysts that are using that feature within GIS to do some of this work.
yeah, I'll be full disclosure here. I'm not a GIS expert. I work with individuals in our office, and we provide the criteria to do it, and then they plug it into spatial analysts. But spatial analysts is okay. Yes.
I know there is a lot of watershed modeling out there for programs that you can get. And yeah, I know you're not a GIS specialist. Maybe you could talk about why you chose the one you chose.
Greg might be better. He is a GIS expert.
I would not say I'm an expert. I'm moderate level. Greg Jameson in our office puts me to shame, and he wasn't able to be here today. But so we do have those resources. So are you talking like water quality modeling, or are you talking more like watershed delineation,
Well, the
kind of
program-
GIS modeling?
Yeah, the program that you used with your Excel spreadsheet and going back and forth.
Oh, okay. Well, I guess there's really two facets to that. On the GIS side, Greg Jameson in our office was actually used to use some of the spatial analyst tools to delineate those watersheds. So we're actually able to take the information from the lidar and let the lidar do the hard work, let the GIS do the hard work of processing that topographic information and breaking down that into individual watersheds. So we didn't have to go through and trace around and try to figure out ourselves where the watershed boundaries were. The program actually did that. We were able to ground truth that too. Stepple was the model that we used on this project. It's a spreadsheet-based program. It was what was recommended to us by the DNR. The nice thing about that project or program is it's really good on these smaller scale watersheds because you can input field scale practices. I can tell it in this sub-watershed, I'm going to put this many grass swales in. I'm going to put this much stream bank restoration in. And it'll do the calculations to figure out what the load reductions are. On some of the larger scale watersheds, you might use a program like SWAT or some other things that kind of do a more broad-based approach where it's like, well, we're broadly going to put these practices in over a larger watershed area and then have it calculate the results. So there's benefits. I think you have to go with every different project case by case on which type of modeling software you want to use.
Any other questions?
I got talking about modeling. I'm sorry. Yeah.
I guess on the modeling, if you have BMPs that you're proposing to improve water quality, how would you do that in Step L if it's kind of a simple model? Did you find input?
Yeah.
What's your
Yeah,
strategy?
it has spreadsheet tabs that you can input the types of BMPs you have, and then you input the expected load reductions from those. So we use the information from Iowa's nutrient protection strategy, which is updated every year on what the expected load reductions of the different practices are, and we're able to put that into the model, and then we're able to tell it which areas in that sub-watershed they go, sub-area, and we want to reduce nitrogen and phosphorus pollution by this much. We were able to put in our assumptions and tweak the model, and it took a while to kind of be like, okay, well, we put this many practices in, oh, we're not quite there with phosphorus, or we're not quite there with nitrogen. We need more practices. So then we put them in different areas, move them around, and because of the program, we're able to do that fairly quickly. Iteratively, move it around, change a little bit here and there, and finally we got a solution that worked, and we were able to then put that in our report.
On the urban side, one of the things we didn't talk about is we actually, one of the things was we wanted to see results on the landscape sooner than the next 30 to 50 years, in terms of these plans are going to take a long time to implement. So we actually zoomed into the 2,000 acre sub-watershed scale, and in that case we used, I believe, you used ArcSlam or actually ArcSWAT, or SWAT. Windslam, thank you.
Windslam for some of the urban practices.
And really, within those 2,000 acres, modeled it to a point